Hello everyone, my name is Sayak. I work as a machine learning engineer at Carded. I'm really excited to be here today.
Hi everyone, I'm Nilabro. I'm an NLP engineer at Carded. It's a pleasure to be here.
Today we'll be talking about improving data flow pipelines for processing text data at scale. And our hope is that by the end of this session, you will leave with a couple of recipes that you could use in order to optimize your own text processing pipelines for data flow. We have a packed agenda today. We'll be starting off with the problem statement. Then we will go over the kind of tools that we used in this particular project. Then we will walk you through the unoptimized text processing pipelines. And then Neil is going to take over and he will walk you through the components in the pipeline that could have been improved. And we will also share with you the improved pipeline and the results that we were able to get out of that improved pipeline. So we really hope that you get to take some recipes for optimizing your own text pre-processing pipelines with Dataflow. So without any further ado, let's get started. All right. Let's go over the problem setup quickly, where we will discuss the kind of inputs that our pipeline expects and the kind of outputs it's gonna provide. So the inputs to the pipeline are raw text pieces comprising of multiple sentences. Our ultimate goal is to be able to train a machine learning model for text classification on these inputs. But before that, as you might know, those raw text pieces are needed to be converted into a format that is easily understood by the underlying model. And this part is known as data processing, which is what we are going to be covering in this session. But we will not be covering the actual machine learning model training part in this session. So as a part of the pre-processing routine, we will be first tokenize a given piece of text, and then we will be generating text embeddings for that uh, text piece with a pre-trained sentence condition model. And since this operations can be performed in a row by row fashion, we will leverage Apache Beam in order to construct a pipeline which will take care of orchestrating all the necessary components, starting from data ingestion all the way to data serialization. So let's quickly go over the kind of different tools that we will be using. So our inputs will be coming from BigQuery. We'll be using a tool called Sentence Splitter. It's a Python library which we will use for splitting a piece of text into sentences. Then we'll be using a tokenizer and embedding model from TensorFlow Hub. Our tokenizer will be a word piece tokenizer, and the model is going to be a sentence condition BERT model. We will use Apache Beam in order to pack the different processing steps into a pipeline, and then we will use Cloud Dataflow as the pipeline runner. Also, as you may already know, an Apache Beam pipeline can also be executed with other executors like Apache Airflow, but for the purpose of this session, we'll be using Cloud Dataflow, and we'll be using Google Cloud Storage for saving the artifacts. So let's now take a look at our unoptimized text pipeline. So again, just to recap, this is how the pipeline looks like. We will start by reading the data from BigQuery. We will then pre-process a given piece of text using a pre-trained tokenizer. Then we will generate embeddings from the tokenized text piece using a pre-trained model. Then we will serialize the embeddings as binary strings, and then we will finally write those binary strings as TensorFlow records to a Google Cloud Storage bucket. And in terms of code, this is how this is kind of the schematic of how the pipeline might look like in terms of code. So here we are just reading the data from BigQuery, then we are just mapping a function that takes care of the tokenization and the embedding generation from the raw text piece, and then we are basically serializing the generated embeddings as TF records, and finally writing it to a Google Cloud Storage bucket. Now this is a heavily unoptimized pipeline, but I will now hand it off to Neil, who is going to discuss the optimizations that we performed in order to improve the runtime of this pipeline. So Neil, take it from here.
Thank you, Shayok. So, in a batch of uh, in a batch of sentences of uneven length, the common strategy is to pad the sentences with a special padding token, so that all the sentences have uniform length, which makes it possible to apply tensor operations which will be used in the models. And in our case, we could pad the sentences up to a length of 512, which is the maximum length for a sequence accepted by our encoder. But this method would result in a loss of performance, as compute would be wasted on processing the padded tokens, denoted by the yellow rectangles, when sequences have a length less than 512. A fairly common trick used in NLP is to minimize compute waste due to uneven lengths of sentences is to first sort the sequences on the basis of their length and then batch the data, resulting in batches that require minimal padding tokens. We could apply the same strategy in our Beam pipeline for performance gains. So let's have a look at how the improved pipeline looks like. So first of all, we tackle variable length match sequences. It's clear that we would reduce some compute waste here, as we have managed to get rid of an entire column of padded tokens in the first image on the right side, just by padding the sequence to the maximum length per batch rather than using a global maximum of 512. Once we sort the sentences on the basis of their length and only then perform batching, the reduction in the proportional padding tokens per batch is drastic, as can be seen on the right side of the image. So we essentially break down the step of tokenization and encoding, which was a single step in the previous Beam pipeline, into these three different steps. We first tokenize using a part do step followed by batching. And in the last step, we perform sorting, batching plus padding, and in the end, encoding. Substep 2 is important because it creates a batch of sequences which are then sorted and batched again before encoding. Without this step, we would have to wait for the pipeline to finish tokenizing all the sentences first, and then use or possibly write a P transform to sort all the tokenized sequences. Apache Beam selects the batch size from within a given range on the basis of the downstream performance of the pipeline, which is an added bonus. In substep 3, one thing to keep in mind is to unsort the embeddings once the batch operations are done. So this is how it looks like in code. As you can see, we have separated the three different components of a single step, and which results in much performance gains that we will be discussing in the future slides. Now let's look at the performance gains. Here, the unoptimized pipeline uses fixed length padding, and thus all sentences are padded to a length of 512. Hence, from 3 days to 11 hours, we bring down the wall clock time down to 2 hours and 36 minutes. For a deeper look at our work, you can check our blog post and our code. We would be happy to get any feedback. With this, I end our presentation. Thank you all for attending this talk and for your patient listening. Please feel free to ask any questions. Not sure. No, nothing comes to mind.
All right, cool.
Thank you all for attending our talk.